A very good afternoon to all of you. Once again, good afternoon, Manu. Good afternoon, Oliver. I hope you all can hear me clearly and see my screen. Good afternoon, Chintan. I hope your Chintan Manan is going well. So, in today's class, we are going to talk about noise removal. We are already talking about noise removal, and in the last few lectures, we have seen noise modeling, noise parameters, how to assess them, and in the last class particularly we discussed various kinds of filters and how to implement them to reduce the noise. Now today's class we are going to look at one more way to reduce the noise, and that is the Fourier domain, or that is the periodic noise removal. If your noise is random, Gaussian, if your noise is salt and pepper, we have already learned how to remove them. Periodic noise is a bit nasty at times. Removing them is not easy in a spatial domain, but thankfully, removing them in frequency domain is very straightforward. Today, I'm going to talk about it. In the first part of the lecture, I'm going to talk the theoretical aspects, and in the next part of the lecture, I'm going to talk about the demonstration. I'll give you a small demonstration how this works out on different types of images. So that's our topic today. What are periodic noise? How do they look like? How to identify? In what different shapes and sizes they can come in? And then we will learn, understand how to use noise removal using FFT, fast Fourier transform. Most of the computer algorithms which implement Fourier transform is use an algorithm called fast Fourier transform, or in short it is called FFT. So going ahead, how does the periodic noise look like? So periodic noise repeats itself at a constant frequency. Remember, whenever I'm using the word period or frequency, I have already discussed to you people that we are not talking about the time. We are not talking about time period, or we are not talking about time one upon time. What we are talking about is a space here. The image is a spatial phenomenon. It's spread out in space. It does not change with time. So we are talking about separation between two parameters, or if your image has objects which repeat at constant frequency, that means at a constant spatial interval. If they repeat, when I say frequency here, then number of repetitions are in a unit intervals, spatial intervals. So if they repeat, then the noise comes in the category of periodic noise. The I will just show you one example here. So you can see here that your these lines, bright and dark, they repeat at a regular spatial interval. So separation between these two lines in pixel will constitute the period of the noise. And if you take some unit distance, the number of such lines in the unit distance will constitute your frequency. So that unit distance could be anything, 1 pixel to 10 pixels, etc. Now, this noise is, you can see that your objects in the image are fairly large in size. One of the smallest image, this man standing here, you can see that it's much larger than the size of the noise. There are multiple lines here. So size of the objects versus the period of the noise is a parameter. If this difference is much, if the period of the noise is small and the size of the objects are large, the difference is much in terms of number of pixels, then the separation is very easy. However, if the period of noise is as large as the size of the objects, then separating them becomes a rather challenging task. So remember that. Directionality of the noise will matter. Here the noise is inclined. It will be seen in one way in your Fourier domain. If it is vertical or horizontal, it will be seen in some other way in the Fourier domain. So the directionality matter. The strength also matter. This black is how much black, white is, or this gray is how much dark, or this white is how much more bright. That also gives the strength to the periodic noise, and that also matters. So these are the parameters. Let us take some more examples where we understand the periodic noise. So this is another one. You can see that it has a almost the strength, similar strength periodic noise, but it has horizontal lines. All lines in this case are horizontal. You can easily see that here it is the period, the separation between the two lines matches some of the image elements. For example, the lips. So width of the lip and the separation between the lines, they match somehow. So when you will do the noise removal, you have to be extra careful about these areas. Other is eyebrows. The dimensions of the eyebrows match with the time or the period of the noise, or the separation between the two lines. Some of the eye elements and ear elements are also, or nose elements are also matching. So in this case, you have to be careful or observant that if you are removing noise, perhaps you may remove some of the object elements as well. So be careful there. This is another one where the strength of the periodic noise is very strong. This is much darker and this is much lighter. A very casual observation also will tell you that this is sinusoidal in nature. If you plot an intensity graph, if you ignore the handwriting, and plot an intensity plot. So if you plot an intensity plot, then what you will get is a sinusoidal plot here. Intensity drops, intensity rises, drops, rises, drops, rises, drops, etc. So that's another one. You can see the noise here is periodic noise here is vertical appearing, and directionality strength, it's more powerful, but lines are separated by a larger distance. So the period is more. Their period can be measured in pixels from here to here. So period is high, frequency is less. It's a low frequency noise. In fact, if you are careful observer, the writing is close here. So here the writing is a high frequency component. Your image subject is a high frequency component, while image noise is a low frequency component. So you can see it's slightly revert. In the demo session, I'm going to deal with this image, so please wait that till that time to see how this we remove. It could be challenging at times. There are other ways also to deal with this that we may learn later, but we will see how Fourier transform how much Fourier transform is effective to remove these kind of noises. And I have one more here, that if you look at this is some curtain, I guess, old photos clicked by me in the film days, and then I scanned it. I scanned it using a scanner. Now, all the flatbed scanners, if you're using, they are going to give these scanning lines. any old photo at your home, if you scan it on a flatbed scanner or if you get it scanned, you will get these lines. These are the scan lines, in a sense that the scanner has LEDs which are arranged in a row, and as LEDs move, they throw the light is reflected, and these scan lines are created. So that is another example. So we are going to look at this example. Now, how to remove these noises? So removing these noises is very simple and straightforward. Thankfully, because of the frequency domain analysis, which is as a tool available to us. So periodic noise appears as concentrated bursts of energy in Fourier transform. So it's a concentrated burst, and you can see them, you can pinpoint them, you can spot them in the Fourier transform image of the original. So that is easy to do. Once you locate, and their location will be corresponding to the frequencies. Remember, most of the Fourier transforms are plotted from the center onward. So then higher frequencies come close to the, sorry, um, higher frequencies go away from the center towards the periphery, lower frequencies come close to the center. So depending on where you see the burst of energy in FT, you will identify or locate, or you can guess that if it's noise. Maybe with experience that guess becomes better. In the beginning you may have some errors, and you have to sort it by using trial and error. Once you have identified your noise, then you can use a selective filter. So use some filter. uh, Basically most of the time we use band pass or band reject filter, or sometimes even notch filter. So one of those filters can be used to remove the noise, and then take the inverse Fourier transform to get your final image. So inverse Fourier transform will bring you from frequency domain to final image domain. So let's see one of the examples. One of the example is here. This is my original image, the moon, person on the moon, and it is corrupted with a slanting periodic noise, a noise which is almost at 45 degrees. Here is the Fourier transform. Can you guess, in this Fourier transform, where is my noise? Chintan, Manu, Oliver, Prasoon, anyone? Can anyone guess that in all these, where is my, in all these white spots, where is my noise? And if you have heard my last lecture on Fourier domain, perhaps you should be able to answer it. So, can anyone guess and tell me? Because this guess is very important, because once you guess it properly, removal will be easy. If you can't guess the noise, then you may delete some other component, and you may get some odd results at the end. So you have to be very, very careful. Along the diagonal. That's right, Chintan. Along the diagonal. Remember we started in the Fourier domain with the single slit pattern, and we had seen that the Fourier transform of a single slit is perpendicular to the slit. So here the lines are inclined this way, the periodic lines. So energy burst perpendicular to these lines, that is this way, would be your noise. So that is one of the hints, that is one of the signals by which you can identify noise. Manu, you are saying something, lines would be converted into points in FT, right? So all the dots are noisy. So that's a good question, Manu. What happens here is, what happens over here, what's my guess over here is, that this is not a single frequency, but it has harmonics. So had it been a pure frequency, it would have appeared as one dot here and one dot here. But since it may not have that, but instead it may also have some sort of harmonic structure underneath. So those harmonics are appearing across the diagonal. Now, why is it so? I don't know. I took it from the book, but I took a screenshot. So my one of my guesses is that if I when I take a screenshot, remember I don't know how these screenshots work. They give certain pixel by pixel, but then those are not the original pixel of the image, but they are the pixels of the LEDs on the screen. So screen LEDs might be giving some more harmonic to the original image. The book says that this image originally does not have an harmonic. It has only fundamental frequency, which appears as two dots, one on this side and one on this side. But a screenshot of it gives me this way. So I am assuming that these are definitely harmonics, and these are coming because when you take the screenshot, the background LED pattern might be doing, or the way the pixels are arranged on the screen, that might be doing some trick. So I mean, I think on Gonzalez and Woods have a website. I think digitalimageprocessingplace.com, something like that, and they have this image available there. So you can get the original image and perhaps work on it. Might give you better results. So think about it. But yeah, identified correctly. That's right, Manu. So identified correctly, the noise is slanting, so the Fourier response will be this way. So obviously our aim is to remove these Fourier responses. So successive, I don't think so, Aditya. One has to check, but I don't think so, because one, suppose if my theory is correct, then one screenshot gives me these harmonics. Now subsequent screenshots will give me the same harmonics because the underlying structure is the same. So after first screenshot, next screenshot should not degrade it much as far as these harmonics are concerned. But one has to do and see. I have used ImageJ to get this. As I said, for a quick check, it's a very good tool. So you people can use that, and you can use that and check your hypothesis. So yeah, going ahead, this is my, so I tried removing, so I can use a notch filter here. So I removed at least fundamental and the first harmonic on either side, and then was feeling a little bored to remove the other harmonics. I stopped there, and then I took an inverse Fourier transform, and once I took the inverse Fourier transform, this is what I got. You can see that some of these noise is still remaining, but majority of it is gone. Borders, some is remaining. Why are they remaining in border? I leave it to you to figure it out. Uh, Maybe removing these harmonics further will make it much cleaner. I mean, for comparison, I have the two images over here, and you can see the difference. You can see that almost 90% of the periodic noise has gone in this. That's a very good improvement, I would say. So no other method would have given me such a strong tool to remove these kind of noises from the original image. So yes, so maybe I can stop my theory lecture here, and thank you for that. And then maybe we can go to image J, where I have my rest of my images on which we can work. We can now go to image J and we can work. So this is my image J, and now we can work our rest of the images. So you can see right now that this is my original. I have taken an FT and I have got an answer, which I have already shown to you. Now it's time to close this, and go to the other image. So all my images I have taken kept here. So let me keep it there, and no, not here, and this, and file, and I'm say open, and then I'll go to the next image, which is of the man's face. So this is a horizontal image. So obviously the Fourier spectrum will go vertical. So I can go to process, I can go here, I can take an FFT, and you can see that how the Fourier transform appears. Look at it carefully. Now it is a burst of energy perpendicular to the periodic lines. Here the lines are horizontal, the bursts are perpendicular. So I'm going to remove the high frequency, I'm going to remove the noise components. So let me be adventurous and remove all the harmonics at once. So I've removed all the harmonics by being more adventurous, and see what do we get. So I can go to process, I can go to FFT, I can say inverse FFT, and you can see here is my difference. This is my original. If I can put everything on the screen, relevant part, then this is my original. This is FFT, removed the noise component, and you can see here. You can see that it has not created much problem in the lips area, but some problems are created over here, and some problems here also. Not that much sorted out. So that is how it will give you your answer. You want to see what happens if I reduce more? Let's see. We can have um, some fun here. Fun in a sense that it's always wise to do some trial and error thing and figure out. So I'm removing if any other source of noise is present. You can actually make a circular uh, filter and grow it, and it happens easily that way, but I'm just taking a long step. Actually the majority of data is centered, so I can just remove everything, leaving the small center part, and see what results we get. So I leave it here, and let's see what results we get, or does it give any result. So you can see that it gets distorted. A lot of distortion comes in. So we have eliminated lot of, not only just the frequency, but lot of other image components also, and that brings a lot of distortion. That's right. We can take one more image. Remember, Fourier transform only experience will teach you. You can do by calculation, but I would suggest go by experience. Experience will come only with practice. Practice happens only when you are initiated. I'm doing that job of initiating you in this process, and after that you people can explore it further. So I will now take the challenging, one of the most challenging images, the Xerox one. Here the challenge, as I had said, not in that strength of the noise or directionality, but the periodicity. The noise has a lower periodicity, and these writings are very close, so they have a higher periodicity. So it's a it's a reverse thing happening. So it's challenging in that way. So I can just take an FFT, take an in, no, sorry, press something wrong. Process. F50. And take an F50. And you can see that it is really challenging. Where is the noise in this? Can anyone tell me? Manu, Aditya, Chintan, Prasoon, and other people. Where are other people? Pankudi is there, Nimita is there, Namita, I guess, sorry, and Pinak is there. So many people. Where is noise in this? And where is writing? It's a lot of blurred out. Looks like clouds. Yeah, one of the challenging images that we have, low frequency noise and a high frequency writing. Even writing does not have a frequency. In fact, writing are random. That is why you will get this cloud. There are no patterns. Horizontal line. I doubt horizontal lines. To tell you the my guess is that my simple guess is that what you are having is your if you zoom it, my guess is that the intersection point, these are my noise. That is my guess. Because the noise has a image, overall handwriting does not have a strong periodicity. That is why it looks like a cloud. You can see this cloudy structure. But if you noise has a strong periodicity, and noise periodicity is lesser than the writing. So I will going to remove these two notches, and of course it has some harmonics also, and take my chances. What happens if I remove this? So one is gone. Other one is gone. So let's remove these two and see what impact does it bring. Ah, this is what you got. Check it out. You can see that handwriting is untouched, almost untouched. But all the black lines have vanished. The white lines also have vanished if you notice carefully. They both have heading towards gray part. So this is how it works. Can I be a little more adventurous here? I think I can extend my lecture up till 1:30 and do some adventurous things. Let me remove this also and see what I get. And one harmonic looking structures. One harmonic on this side and one harmonic on this side. Remember, this is you are now operating at pixel level directly. If you are not convinced, you can see that these are individual pixels. You can actually count pixels and delete. For example, if I want one pixel more, you can do that. I don't know, it's not stretching. Okay, I pressed the wrong button here. Yeah, so if you want to increase one pixel more here, one pixel more, you can one set more, you can do that. If you want to increase the length by one pixel, you can do that. So now this is how my filtering look like. You can now see. Now I can go ahead and take an inverse. Go to F50 and see if it gives me slightly better result. maybe perhaps slightly better. So you can see that your handwriting has becomes, all these lines have gone, it is much more legible. So if you are a forensic expert and if you get a document like this, you are perhaps can convert into a document like this, then bringing in thresholding should solve this image problem. Let me see if this works out. Binary, correct? Thresholding is binary. You have to take a histogram basically and figure out how the thresholding will work. You can see this is my thing. So you, the image handwriting is towards the darker side. So if you threshold it somewhere here, you can extract the handwriting. So that is the idea. I go to process, I go to binary and make binary. Yeah, it does not give me any control, but you can see that it has extracted the handwriting part from this. Can we do make it better? I don't know. Let me just try if there is any other tool available. Sharp, smooth, edges, maxima, enhance, noise. Hmm. No, there are no options here. Binary does not giving me any control. But in binary, remember, you can always, uh, by writing a software, you can always decide at what point you are taking, and you can do. Here it's doing a reverse binary. In fact, I wanted writing to be in black and rest in white. It's doing ulta, it's making the writing in white and rest black. That is why a lot of distortion has come in. In fact, you can see that these lines are breaking everywhere, which actually can be removed by a process called wait. So if you have maxima noise, then if by a process called dilate. We have not done dilation and erosion, but that they join these dots. So a couple of dilations perhaps will make this happen. So yeah, a lot of things can be done. Maybe we can stop working on this image and take the last image to end the lecture. Now the last image, don't save, file is the image. What do I take? And there is an image for the curtain and there is an image again for multiple noise. So I'll take the image. Yeah, you can use the smoothing mask. So as I said, all those steps are available further, but to begin with, here it is, since we are right now focusing, I'm not getting. So I have two images over here. Let me open both of them. This is curtain, and as I had shown you, I need to convert into an 8-bit grayscale. So that is done. You go to process, go to FFT. These are the high frequency horizontal lines. Then you can see these bursts appearing. These are my bursts. These are the high frequency original lines, horizontal lines. The bursts appearing on vertical axis, and then there. This is the first one. This is harmonic, etc. There is a slight slanting here also, and because of which there are slanting lines appearing here also. This slanting line should correspond to this slanting line, and this slanting line should correspond to this leafy structure. You can see this line is perpendicular to this. This line is perpendicular to these two lines. So remember, Fourier transform Unless you are experienced, you will not be able to identify what is your image and what is your noise. It becomes really a shot in the dark. So listen to me carefully, practice it on different images, and you should be able to address it. So yeah, the noise is horizontal thin lines. Remember, it's a low frequency. So they will appear at a farther distance. This is a high frequency noise. These are the harmonics. So all I do is remove these quickly. Remove this one. So I removed all four, and then I plan to now take the inverse Fourier transform. Yeah, so now you can see the difference here. The lines have almost gone. This is my original. This is my transform. In fact, the lines here have so much vanished that you can see the fabric of the curtain as well, which has a still higher frequency than these noise, which I have not deleted thankfully. Maybe these are the bursts which represent the fabric, curtains fabric. So thankfully I have not removed this. You can see very successfully you have removed these noise. The rest of it is still there as it is. Okay, now just to conclude, I will show an image, but maybe I will not get into it further. And that is an image where you can have multiple periodic noise as well. And then in that case, it becomes sometimes tricky, sometimes fairly challenging. So this is, you can see if you observe this phenomenon, this is a very tricky image. Why is it tricky? Because if you observe it, you will find that it has one variation. This is a super large variation. It's a very high, very low frequency noise. You can see this variation. So this variation is a very low frequency noise. But apart from it, it has a very high frequency noise also, these dots. And these dots are multiple directional. If you observe carefully, these dots are coming this way 45, these dots are coming this way 45. These dots are in black, these dots are in white, so multi-directional. While these variations are large, and somewhere in the middle you get the image structure, subjects, buildings. The windows are smaller than these larger variations, but larger than these smaller noise details. So it's a fairly challenging image for noise removal. Maybe I will share this image with you, and you can use the skills learned in this lecture to eliminate noise from it and see how it works out. So thank you so much for this lecture. We can stop here. Thank you. I will come to the group Google Meet, and if anyone wants to discuss anything, we will discuss and talk about it.